business item, and then our pleasure is to welcome Dr. Matthew Duez, who is a professor here in the department. Been here since 2010, believe it or not. I don't believe it. But yeah, he got his PhD in 2005 from University of Illinois, Urbana-Champaign. And then he spent a while as a postdoc at Cornell. And then he came here as faculty. And during those years, he worked on the same broad topic, which is general relativity in very extreme environments, such as black hole neutron star mergers and neutron star mergers. And he is an expert in the Einstein spectral code, which I'm sure he will mention. In this talk, thank you for talking, and the topic is extremes of physics in black hole merger, neutron star merger.
Okay. Thank you. Do I have to be in some particular place for it to hear me?
It should be fine, anywhere down there.
Okay. All right, thank you. So it was around third or fourth grade when I decided I wanted to be a physicist when I grew up. And so I got some books from the local library, right, for lay audiences. And they explained to me that there are four fundamental forces: strong nuclear, electromagnetic, weak nuclear, gravitation, right? Most of the time, you don't need to take into account all of them. And most of the time, they're all in some sense weak. But there are some energetic violent events in the universe where they're all important and all in senses that I'll try to make clear strong. And among these are when a neutron star collides with another neutron star or with a black hole. So let me give you a quick review of the phases of a black hole neutron star merger, right? A black hole and a neutron star are going to come together. The neutron star is going to get ripped up and we're going to end up with just a black hole. The story for two neutron stars merging is actually fairly similar. Okay, so we're going to start off our story with our two objects, our black hole and neutron star. They're far away from each other. They feel each other's gravity. They're in orbit around each other. Now, if Newtonian physics was like the ultimate truth, right, the full truth, and we could treat these objects as point masses, then, as you know, they would just orbit each other forever, right? Because, we know that the solution to the equations of motion for 2 point masses feeling each other's gravity when you got negative energy is elliptical orbit. Right? But general relativity predicts that if you have accelerating masses, there will be these ripples of space-time curvature called gravitational waves that will carry away energy and angular momentum. As the binary loses energy, the two objects will be forced to sink deeper into the gravitational potential. They'll have to get closer to each other, spiraling inward. Eventually, they will get very close to each other. And so this in-spiral phase will be terminated in one of two ways. Either the orbit of the neutron star around the black hole will become unstable, at which point the neutron star just plunges into the black hole. Or the neutron star gets so close to the black hole that the black hole's gravity, the tidal forces from the black hole's gravity are strong enough to rip the neutron star apart. It goes ripped up into this swath, like in that second picture. And a lot of the matter streams toward the black hole, and some of it flies off into space. Among the stuff that doesn't fly off into space, that's bound, some of it has enough angular momentum to avoid falling into the black hole. And so that gas will fall into orbit around the black hole, forming a sort of donut, torus-shaped structure called a disk. And this stuff cannot fall into the black hole because there's a centrifugal barrier. So you might think again, well, then it's just stuck orbiting forever and ever. But something again happens, and this time it's not a relativity thing. It's a hydrodynamic thing, a magnetohydrodynamic thing. This fluid flow turns out to be vulnerable to certain fluid instabilities, which trigger turbulence. So you have to imagine this flow is churning with turbulent eddies, and the net effect of this churning is that angular momentum gets handed off from the gas on the inside close to the black hole to the gas on the outside further away. So as gas on the inside loses angular momentum, it moves inward, falls into the black hole. As gas on the outside gains angular momentum, it moves away, and the disk spreads out. So that's the basic idea. So now the physics players. Let's take it according to those four forces again. You start off with gravity. Usually that's the last one people mention, but I'm a relativist, so I put it first. So gravity is the manifestation of space-time curvature, right? And so space-time curvature is what determines what counts as inertial motion, how objects move if they're not pushed. And in particular, it determines how light rays move in space-time. So it determines the light cone structure. And the light cones determine which events can influence which other events, right? In order for something that happens at one point in space-time to influence something that happens in another point, the first event has to be within, the second event has to be in the future light cone of the first one. So it can happen that the space-time curvature is so strong that it tips these light cones, like you see on the top, so much that there's this region of space-time, a region of space, you'd see inside to the left of that dotted line, where information cannot get from the inside to the outside. So this region has cut itself off from the universe. It's become what we call a black hole. Another manifestation of strong space-time curvature that we've already mentioned is that you can get powerful energy escape from gravitational waves, these wave-like distortions of space-time. The strength of gravity can be measured by a dimensionless constant. Here it's basically mass divided by radius. And it's around 0.1 to 1 only for neutron stars and black holes. For regular stars, it's more like 10 to the minus 6. So I move on to the nuclear force, right? So this is the force that is holding nucleons, protons and neutrons together to form nuclei. The density of matter inside atomic nuclei is around 10 to the 14 grams per cubic centimeter. This is also around the density inside of neutron stars. You'll notice that that's a whopping big density, much higher than the densities that we're used to in daily life, right? And the reason for that is that, for ordinary matter that we're used to, the nucleus takes up only a small fraction of the volume, even though it takes up most of the mass, right? So you could imagine that if you could take ordinary matter and compress it, right? So you got rid of that space between nuclei, made the nuclei touch each other, that you would have something that would be similar to the matter inside of neutron stars. Okay, so the main property that we will be interested in for neutron star matter is the so-called equation of state. This is the equation that relates pressure to density and temperature. The equation of state that you'll all be familiar with is the ideal gas law. Inside of neutron stars, we do not have an ideal gas, not even an ideal Fermi gas, because these nuclear forces are so strong. They create extra pressure. In fact, the equation of state deep in the core of a neutron star is still something of a mystery, still something that we are trying to constrain in various ways. In the accretion disk, right, so after we've shredded our neutron star and you've got that gas swirling around, densities are lower. So this unknown high density equation of state is no longer an issue. You actually can think of that disk as an ideal gas. In fact, it's several ideal gases of free nucleons, right? Protons and neutrons, and also various atomic nuclei, electrons, positrons, photons. Now, you might worry that I said nuclei, lots of types of nuclei. Isn't that going to be a whole lot of different variables to keep track of? There are a lot of different possible nuclei, right? Every isotope of every element. But luckily, at these extreme densities and temperatures, nuclear reactions happen very quickly. So quickly that the abundances of the different nuclei types all quickly come to and hold at their equilibrium values. So, so basically, yeah, there's a number for the mass fraction of every different type of nucleus you can think of, but these are not free variables we have to evolve. They're nailed down by equilibrium. You notice, by the way, that this is a type of equilibrium that is not true for ordinary matter, right? We ourselves are not in nuclear statistical equilibrium. If we were, we would all be made of iron. So, but in astrophysics, we encounter every different regime of physics. So you got to always be asking yourself, okay, you know, what assumptions are valid, what are not, right? You know, what types of equilibrium are we in and which are we not? There are actually, accretion disks around black holes where the density is so low, you can't even assume Maxwell-Boltzmann statistics, right? So you got to always asking yourself these things, never assuming. Weak nuclear force, what this does is it changes neutrons into protons and vice versa. A lot of these reactions generate neutrinos. And in fact, the radiation of neutrinos, off of our hot star or hot disk is in fact the main way that our main cooling mechanism. So you can try to emit electromagnetic radiation, but the mean free path for photons is so small that it's very inefficient. Neutrinos are the way that we can more efficiently cool. Now, neutrinos carry away not only energy, but also lepton number. They change the composition of the thing that's emitting them. So we keep track of that by looking at this number called the electron fraction, YE. And what it really is, that doesn't actually have anything directly to do with electrons, except by charge neutrality. What it really is it's what fraction of the nucleons are protons as opposed to neutrons. Neutron star matter, as you guessed from the name, is very neutron rich. YE inside of a neutron star is around 0.1. There are some protons, but there are more neutrons. Finally, the electromagnetic force, right? So neutron stars can have the strongest magnetic fields naturally found in the universe. And they, especially when two neutron stars merge, you can get very strong fields. Also in these accretion disks, the turbulence will wind up strong magnetic fields. And in fact, the magnetic field plays a crucial role in generating this turbulence that drives accretion. But they do something, the EM fields do something else very interesting that you'll appreciate. They provide a way of extracting energy from the system. And this is not through radiation, but you'll recall that even a non-radiative electromagnetic field can have an energy flux associated with it, right? Remember, this is the Poynting vector. E cross B tells you this energy flow in the E and B fields. So this actually gives us a way that you can extract energy from a black hole, right? If you have magnetic field lines sticking into the black hole, right? This E cross B thing can be pointing outward, right? So you can have energy flowing out of the black hole. And that's totally okay because there's no material or radiation stuff that's coming out. And this, so ironically, black holes can end up black hole systems, not black holes on their own, but black holes surrounded by gas can end up being some of the brightest phenomena in the universe, right? Things like, including active galactic nuclei, like we heard last week, but also gamma ray bursts, like are made from these mergers. All right, so all of physics is in play here. But really, that's always the case, right? In any real physics problem, you can't just, it's not like sitting down to your E&M test and this is an E&M exam. I know what type of physics I need to use and what I can just ignore, right? So, the reason that might seem intimidating is because of how we learn physics, right? So, the way that you learn physics is first you take these 4 core subjects you study, right? Classical mechanics, classical E&M, equilibrium, statistical mechanics, and non-relativistic quantum mechanics. Each of these subjects has, its own approximations that go with it. Each of it has its own math, its own tricks that have been optimized to solving that type of problem. But the result of this optimization is that it almost feels like 4 subjects, like they don't have much to do with each other. So it means that your education has to have a second step afterwards, where you sort of restore the unity of your perspective. And that has 2 pieces to it. Number one, you have to learn to start, not with, I'm doing quantum mechanics or whatever. You start with a problem, a phenomenon you're interested in. And then that problem decides what is the relevant physics, right? So you have to check, do I have to worry about relativity? Am I in equilibrium? And so forth, right? The second piece of this sort of conceptual unification is you start to notice that these different fields aren't quite as separate as they seem at first. There are these sort of bridge concepts and mathematical structures that unite them. Things like the action principle, or symmetries being associated with conserved currents, or connections on vector bundles, right? So we faculty spend a lot of time thinking about and discussing the graduate comprehensive exam. Yeah, I'm actually going to talk about this briefly. I very much respect all the different opinions that people have, but since it's my talk, I'm going to share with you what my own sort of hopes are for the current arrangement, what I hope it facilitates, right? So as I see things, you spend your first year of graduate school taking a deep dive into the core classes, and you get really good at solving problems in those classes. Probably, I'm going to admit, the best you're ever going to be for the rest of your life. Then you take the comprehensive exam. Let's be optimistic. Say you pass it. Hooray, that's great, because that means you got a year left of classes and now your focus is somewhere else, not on how do I solve core physics problems. It's on this sort of unification thing. So you take some application classes, right? Solid state physics, biophysics, astrophysics. And that really illustrates for you how you do this number one thing. Start with the problem, what physics is relevant. And you take classical and quantum field theory. Those are the big classes that do number two, the formal unification of physics, to the imperfect extent that it has been achieved. So anyway, okay. Back to black hole neutron star disks. So that's our problem, right? We got this hot gas swirling around a black hole, hot dense gas. The first step in tackling the problem is we think about the different processes, work out a time scale for each one, right? And so we do some order of magnitude estimates. It turns out for this system, the fastest processes have to do with the forces that the gas experiences. So the main forces are pressure, gravity, and centrifugal force. Any imbalance in equilibrium between these forces will be restored in less than a millisecond, right? I mean, slightly longer if you're further out in the disk. Okay, it's basically the orbital time scale. Now we know that from the electromagnetic signal that these disks survive for seconds. So what that tells us right away is that this gas in the disk must be very close to force balance equilibrium the whole way through. As the gas evolves, right, by, some gas move by spreading, right, and so forth, we move from one force balance equilibrium to another. So other timescales, there is a timescale associated with heating and cooling, and there's one associated with accretion, this moving inward or outward because of angular momentum transport. And there's a bit of a hierarchy there, right? So we might the heating and cooling happens faster, but it's more marginal. So we're not quite sure whether we're going to move from one thermal equilibrium to another. I'll sort of answer that question later on. All right, so here's my first mystery I'll talk about. So this goes way back to when I first became a faculty member here at WSU, and my first PhD student, Brett Deaton. We were doing these black hole neutron star mergers. We were doing the first simulations where we were doing full relativity and we're including the neutrino radiation. So we're really wanting to see what the neutrinos do. How do they affect things? So one thing we knew is that neutrinos change composition, right? Electrons or protons into neutrons and vice versa. Now we start off with, we've shredded a neutron star. So we start off with mostly neutrons, right? So you would think that, well, look, there are more neutrons that can change into protons than there are protons that can change into neutrons. So if there's more neutrons changing into protons, we expect that the electron fraction YE should go up, right? We become less neutron rich, more proton rich. And so we looked at it, right? That's this plot up on top. And sure enough, YE is going up for the first 20 milliseconds. And then it turned right around and it went all the way back down to like 0.1 to around neutron star levels. So we were very surprised and confused by this. It was not at all what we were expecting, but we figured it out, and you can too, right? So here's the thing. So remember here, these are the two reactions that are doing this, that are changing YE. And so there are two reactants in making protons, right? Neutron plus positron makes proton, plus an electron antineutrino. So it turns out what's happening is not that we're running low on neutrons, right? We're still very neutron rich, but we do start running low on positrons. So why is that? Okay, well, here's the way I think about it. So recall your statistical mechanics, and you remember that if you have a chemical reaction in equilibrium, you can do that thing where you take the sum of the chemical potentials of the reactants and set it equal to the sum of the chemical potentials of the products. So we're going to do that. One of our reactions happening fast, being in equilibrium, is electron-positron pairs making photons, and vice versa, the reverse process. These two are in equilibrium. So that tells us that, chemical potential of electron plus chemical potential of positron is equal to 2 times the chemical potential of the photon. Chemical potential of photon is 0, right? Remember, the Planck distribution is just Bose-Einstein distribution with no chemical potential. And so, so that means that, chemical potential of positron is equal to minus chemical potential of electron. Okay, so if we know the chemical potential and we know the temperature, we can figure out the number density, how many of these particles there are per unit volume. And the way you do that is you just take the distribution function, integrate it over momentum space. And since these are fermions we're talking about, electrons and positrons, we use Fermi-Dirac statistics. Okay. Now, by the way, we also know which one is the positive one and which one is the negative one in chemical potential, because we know there has to be charge neutrality. We need more electrons than positrons to balance out the protons. So if the chemical potential of the electron is much smaller than kT, then this mu over kT terms are irrelevant, and there's no difference between these two number density equations. There's essentially the same number of electrons and positrons, and there are lots of both of them. However, if density goes up or temperature goes down so that our gas starts to become degenerate, right? Then when the chemical potential becomes comparable to kT, then suddenly there starts being a difference. There starts being a lot more electrons than positrons. So we're able to have more of these proton go to neutron reactions than neutron go to proton. And so that's why, in spite of what we had expected, YE starts going down. And luckily, even though I wasn't thinking in these terms about, these quantum statistics stuff, the code that I copied had a bunch of Fermi integrals in it, so it was there, right? So when I wanted to understand it, it was all, we just had to look through all of this physics that was already sort of under the hood. By the way, it turns out that I wasn't the first one to discover this. This is an effect that's been independently rediscovered a few times. Still, I was pleased with myself for a while. Let's keep your thermodynamics hat on for a moment. And let's now talk about the thermal evolution of the accretion disk. Now, for looking at how the disk is evolving thermally, I want to look at the entropy rather than the temperature. The reason for that is you'll recall that entropy is much more closely connected to heating and cooling, right, than temperature is. Heating and cooling, right, the dQs in the first law. You'll remember that even if dQ is equal to 0, the temperature can change, right, if you let your gas adiabatically expand or something like that. And there's another similar analogous effect in these accretion disks, because we're in nuclear statistical equilibrium. There are these nuclear reactions, right? As our gas goes down in density, right? The equilibrium state at some point switches from free neutrons and protons to a bunch of alpha particles. And when this happens, it releases a whole bunch of nuclear binding energy. The temperature goes up. However, this is not actually a heating, although there's some confusion about this in the literature, because these density changes happen on timescales slow compared to the timescale on which nuclear statistical equilibrium is maintained. So these nuclear reactions are all happening in an adiabatic reversible way. They actually don't generate entropy. Took me a while to get my mind around that. If I would have been paying more attention in my thermal physics class, though, it would have taken me less time. So what is the actual heating process? Okay, well, the actual heating process comes from the turbulence, right? So what turbulence does is it makes big eddies, and the big eddies split up into smaller eddies, and the smaller eddies split up into even smaller eddies. Energy cascades from large scales to small scales, right? Through this process that Kolmogorov worked out, until eventually you reach a small enough scale that viscosity and resistivity are important enough that they can dissipate the energy into heat. How about cooling, right? The negative dq terms, positive, negative. And it's, of course, it's always how you define them. But anyway, so the things that cool our disk are, one, there's the neutrinos, right? The matter radiates neutrinos, then those neutrinos carry their energy away from them. There's another one. There is advection of hot matter into the black hole, right? Hot gas falls into the black hole. It takes its heat with it. So we can think of that as a cooling process over the whole system. Of course, for individual fluid elements, if you just followed it in a Lagrangian sort of way, that wouldn't really count as a cooling process. All right, so my student Fatima Nouri and I, as far as I know, we were the first people to make one of these thermal energy budget plots, where we just sort of plotted these three entropy changes, on top of each other to see how they compared. The first one's to do it for an MHD numerical relativity simulation. So the thing to look at when you look at these is you compare the radiation cooling term, which is in red here, with the advection blue term, right? So accretion is called efficient if radiation is much stronger than advection, right? So it means most of the energy that gets made by heat gets radiated away, right? It turns into luminosity, right? Whereas energy that falls into the black hole, that's just lost, it just disappears as far as the outside world is concerned. So you can see in our case, red and blue are sort of similar, right? So we're not fully efficient accretion, but a significant fraction of the energy released by the accretion process is being radiated away as neutrinos. Whether those neutrinos can turn into something electromagnetic is another question that my student Ashad Mohammed is working on right now. As time goes on, you can sort of, you can't really see it here, but if you follow it out further, what you can sort of see is that as time goes on, advection becomes more and more dominant over neutrinos. Eventually, as the disk depletes itself, neutrino radiation actually becomes inefficient and our disk becomes advective. The other thing is that we can't, adding the coolings don't exactly add up to the heating. So we never actually achieve something super close to thermal equilibrium. That is, that basically the disk is adjusting itself, right? By angular momentum distribution, too fast for thermal equilibrium to really settle. So by the way, this, talking about turbulence and this cascade of energies brings me to one of these, bridge concepts that I mentioned, these sort of overall ideas that unite the different areas of physics. One of these bridge concepts is the concept of renormalization. So the idea here is, suppose that you're interested in looking at a system on a particular scale, the large scale, and you're not looking at, or you're unable to look at the smaller scale dynamics, right? So, we just sort of integrate over these smaller scale degrees of freedom, and then what we're left with is the large scale, but the large scale dynamics is affected by the sort of some feedback from the smaller scales, right? And one way that smaller scale behavior can affect the large scale is by changing parameters in the evolution equations, right? From what there would be if there was no smaller scale, turbulent type dynamics. So for turbulence, the way this works, again, is like in this picture, we see this is energy in different eddies as a function of the wave number, right? So remember, big wave number means small. And there's this cascade, boing, 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 down to smaller and smaller scales until we reach a dissipation scale. And so so we've got these, on the small scale, there are eddies moving around, right? And so in the 19th century, people like, I think Boussinesq was first, and then Prandtl recognized that there's sort of an analogy here, between turbulence and Maxwell's kinetic theory, right? Where you have transport processes like viscosity, heat conduction, particle diffusion, all coming from the fact that, the particles have some non-zero mean free path. And as they bounce around randomly, they take their energy and their composition with them, right? And their momentum with them. And so similarly, the net effect of turbulence, the small scale turbulence that we are not or cannot follow, smaller than our grid scale, is that there's going to be some effective viscosity, right? We can call it, the renormalized viscosity, which is much larger than, we have this, a nearly perfect fluid. The bare kinematic viscosity is very small. But if we're only evolving the large scales, we have to switch from pure hydro to Navier-Stokes. We have to, whenever we do these long-term, especially 2D simulations, we always add a viscosity, right? And in a paper from a few years ago, I showed how you can add these other transport effects, the particle diffusion, the heat conduction, in a numerical relativity simulation as well. So, working with one of my master's degree students, Courtney Cadenhead, we decided to try a similar sort of analysis with the magnetic field, right? So how is the evolution of the large scale magnetic field affected by the turbulence, the small scale magnetic field that we can't capture? So the way you figure that out is we start off with the evolution equation for the magnetic field. You recognize this first part. This is just Faraday's law, right? But then for the electric field, I'm going to stick in U cross B. B is magnetic field, U is the free velocity. This is, you can set the electric field equal to that in the high conductivity magnetohydrodynamic limit. So step two is we split these U and B vectors into their average, their large scale values, plus a turbulent component, right? So B equals B average plus delta B. The average of the turbulent components is 0, but because this is a nonlinear equation, you're going to get terms that look like products of two turbulent components, and the average of that might not be 0. So in fact, that's what happens if you take Faraday's law and you average it. You get an equation that looks like Faraday's law, but now for the average field. But then there's this extra electromagnetic force term. And this is the feedback of the smaller scale. So now the way that you make a so-called dynamo model, a model of the magnetic field evolution that takes this into account, is you have to specify an equation for this extra EMF in terms of the mean fields, the things that you have access to. And so usually the idea, going back to Eugene Parker, is that we need to have a term that looks like this first term. Delta E is some alpha times B average, because this will provide a source term, and it's going to allow the magnetic field to grow more than it would be able to if we had just a 2D axisymmetric system with no turbulence. So what we did, Courtney and I, is we were using data provided to us from a 3D high resolution magnetohydrodynamic simulation of a black hole, an accretion disk around a black hole. This was provided to us by our University of Idaho colleagues. So Zach Etienne and his colleagues, right? It's great that we've got this other numerical relativity group right next door. And so what we are doing, we're interested in two-dimensional simulations eventually. We want to be able to use 2D grids so we can evolve long times and go for that whole multi-second evolution. So we decided to define the average, the large scale, to be the azimuthal average integrate overall phi, take the average. And so we define turbulent, therefore, as non-axisymmetric. Now you notice this is choice. You can make this cut between average and turbulent in different ways. This is the one that's useful for us. Okay, and so then what we're going to do is, we're going to take this 3D data provided to us by Zach, and then we're going to azimuthally average it. We're going to find out what this extra EMF is, and we're going to try to relate it by least squares fitting for coefficients to the mean fields we have. So sounds like a good idea. It didn't work, but it didn't work for interesting ways, for interesting reasons. Okay, and the reason basically is that the way that this basic way that everyone's been thinking about things, right? That you know the average the average evolution, azimuthally average 3D MHD, it should look like 2D MHD, but then with some extra source to make the magnetic field even bigger. That basic assumption is wrong. Okay, so it turns out what actually happens if you azimuthally average the field is you mostly wipe it out, right? It's like a azimuthal averaging. It's like a low pass filter. Most of the field, the magnetic field and the non-rotational component of the velocity are in the non-axisymmetric field. So you can see here's a nice picture Courtney made where, so that on the right, this is a latitude longitude plot, and that strip on the right is the azimuthal average. And basically averaging, smears out, wipes out the field, except on the poles in the jet region where there really is an ordered axisymmetric field. So we also measured the momentum transport, the angular momentum transport, and we see that it's also mostly carried by the non-axisymmetric field. So in fact, if you want to capture this effect, 2D MHD is actually not the way to do it. Actually doing viscosity is closer to a more adequate way of capturing things, right? And so if you want to take your 2D MHD equations and alter them so that they look like azimuthally averaged 3D, the thing that you do is not add a source to make the B field bigger. What you do is you add a resistivity to make it smaller. And so we were able to estimate the turbulent diffusivity this way by doing 2D MHD simulations and dialing this effective resistivity that we added that represents, these eddy effects. If you want to estimate the source term, the alpha term, we did figure out a way that you can do that, basically using the two Lorentz invariants of the azimuthally averaged Faraday tensor, which I don't know if that's a particularly useful thing to do, but I thought it was pretty. So anyway, this sort of different way of looking at things, right? The fact that really there's almost no mean field in the disk. It's it's all the turbulent field, but there is mean field in the jet. This actually, I think you can find sort of aside mentions of it in a couple of papers. I mean, I know because I looked hard, but it seems like, because nobody ever made a big deal of it, it hasn't really sunk in in the community yet. So hopefully this paper I've got out on the archive today will help rectify that, where we really center it. All right, so I got like 10 minutes left. And so with that, I want to talk about one more problem. I want to come back to gravity. And, because I'm a relativist, right? So this is a question about the propagation of gravitational waves, the waves coming off of these binaries. And I'm going to use some math that you learn in your mathematical methods class. I think we call it methods of theoretical physics here. In particular, that if you have a hyperbolic partial differential equation and you want to study how information travels through your PDE, right? How causal influence, moves between events. The thing you do is you study the characteristic lines and the characteristic fields, right? So let's warm up with the wave equation, the scalar wave equation, right? So I've got a spin zero massless particle. So it just looks like this: partial t squared minus partial x squared of psi equals 0. And I'm going to factor that differential operator like so. And then I'm going to define two new variables called mu and v. And each one is it's some first partial derivatives of psi. And the reason that I choose these two particular combinations of derivatives is because I noticed those are the two combinations that I factored my D'Alembert into. And so so what I can think of what that D'Alembert operator does is one of those terms, right? They commute, so either one can hit first, turns psi into either u or v, and then the other, and so then what you're left with is first order differential equation for u and v. Okay, so why is this interesting? It's interesting because whenever you see differential equations like this, right? Different, partial t plus partial space component. A light should go off in your head. This is the advection. This is the advection equation, right? So partial t minus partial x. We can think of that is a time derivative, but it's a time derivative if you are moving along a line of x minus t equals constant. That is, you're moving to the right, the speed of light. So it means, so this equation, what was it? Partial t minus partial t minus partial x of v equals 0. That just says that v is constant along these blue lines going up and to the right, right? The v information just advects to the right. And similarly, u just advects along the red lines to the left. And one reason that we are interested in these characteristic decompositions is that it tells us how to analyze boundary problems, right? So you can just sort of see here that what you need to do in order to supply boundary conditions is you better provide v information at that left end of your domain, right? And you better supply, so the low x end, and you better supply u information at the right end, at the upper x end, because that way you're providing exactly the information that's flowing into your grid. So we want to do, adjunct WSU physics professor Louisa Buckman and I, working with our master's degree student Marlo Morales, wanted to do a similar thing, but for the Einstein field equations. Now, instead of psi, what we have is we have a spin 2 field, a tensor, call it G. So you can think of it, if you haven't done any relativity yet, as we got this 4x4 matrix, right? And there are wave-like equations for each of the components of that matrix. So you can do a similar thing. You can figure out the characteristic fields and their corresponding characteristic speeds. And indeed, we find that we didn't do this, it's been known a long time, that there is a characteristic field whose information is flowing inward from the outer boundary. So it's called U1 minus in the spectral Einstein code publications. Now, so we have to provide this U1 minus information. However, there are a couple of complications, because it turns out that general relativity is in fact very similar to electromagnetism, right? I mean, this was sort of Einstein's goal. He wanted to do for gravity what Maxwell had done for E and M. Well, yeah. And so G, it turns out, it's rather more like a vector potential than it is like the E and B fields. That is, part of the information in it is gauge, right, rather than physical. So we have to take that into account, that similarly, some of the boundary condition information is not a physical boundary condition, but is a boundary condition on how the coordinates are evolving, the boundary condition on the coordinate evolution. Another analogy between GR and Maxwell's equations is that some of the Einstein field equations are actually not evolution equations. They don't give us how our evolution variables evolve in time, right? Instead, what they are constraints. They tell us how our variables have to be related to each other at every instance in time, right? So for Maxwell's equations, we got Gauss's law, as I put here, and we've also got, the del dot E equals 0 equation. So in Einstein's equations, we have constraints, and so you have some of the boundary information is constraint, it's tied down by the requirement that you don't want to be injecting constraint violation into your space-time, right? Just like if you're evolving Maxwell's equations, you would want to make sure that you aren't feeding in magnetic monopoles through the outer boundary. So Louisa came up with a very clever new boundary condition for, or a way of doing a boundary condition for the physical component of the boundary. And the goal is to use this freedom in setting the physical boundary condition so that we eliminate reflections of gravitational waves, right? When the gravitational wave reaches the boundary, we want it to just pass through, not bounce off. And so she and I worked out a very nice way of implementing this in the form of Einstein's equations that the spectral Einstein code used, where you basically you work with a particular projection of a curvature tensor. And on the right, you can see there's a payoff. What you're looking at is boundary condition error, right? So, so small, close to zero is good. And the red curve is what the spec code currently uses. And the blue curve is what our new boundary condition is able to do. And so this is the 2, L equals 2, M equals 2 component of the gravitational wave, which is actually the dominant piece, right? So this is we're quite happy when we saw this. All right, so some things just to give you a sense of what's going on in my group. I'll talk to you about some things that my students and I are working on. So my student Nishad is finishing up a reply to a referee on a paper that we wrote on basically on how you figure out stability of these of very massive neutron stars, right? So it's going to be published. The referee was happy with it. He just gave us a few things to do. My student Pavan Chawan is working on evolving binary neutron star remnants in 2D for long periods of time to see what they do. Let's see. So we're also working on how you model the effective viscosity from these different MHD instabilities that we find. Nishad is embarking on a project to study how some of this neutrino radiation can be turned back into something you can see electromagnetically by neutrinos and antineutrinos annihilating. Louisa and I are looking at boundary conditions for the gauge component of the boundary condition, and Amla Nanda, second year student, and I are looking at other types of compact objects. So binaries where one of the objects is not a black hole but a boson star. And so these are objects that we don't know if they exist, but if they do, they might actually mimic black holes. We might be mistaking boson stars for black holes. So the question is, if you evolve them to merger, right, can you see differences? Okay, so that's it. Thank you for your time.
Bill Scotland.
Boundary condition discussion. Can you relate this to developments in either finite difference time domain boundary conditions for like non-reflecting things or radiation boundary conditions, or a related problem in finite element? So you mentioned Davis, whatever it is.
Yeah.
Why don't you explain a little more how that works?
Okay.
Because those are the same terms that show up in classical.
Yes, as a matter of fact, yeah. So what Louisa did was she had found this paper written by mathematicians, and they had scalar wave problem in mind. They didn't have Einstein's equations in mind. But it just turns out that asymptotically, there's the gauge invariant field for the space-time. It's a wave equation, right? So you can do the same sort of thing. And so the implementation we worked out, it ends up being basically a Neumann type condition for one of the curvature terms. Okay, so the way I like to think about this thing is that so you can sort of see if you make if you choose let's see, I wish there's someplace I'm getting right here. Let's see if I can reproduce my line of reasoning here. So let's say that I have no, that's not going to work. The problem is this is okay, so you can imagine that ignore these R factors here. and let's just say that you're trying to have a wave equation in 1D, right? And you want the solution at your boundary to be, say, you know, psi is some function of t minus x, right? And so so you can check, right, that if you do the if you look at the derivative, you know, this advective derivative going to the right along you know, so this partial t, oh good,
Yeah.
thank you. All right, so yeah, so partial t minus partial x of some function of x. Second. Oh, yes, so suppose we say it's bad if there is incoming component. No, that doesn't work. Let's see. Did I? No, I think I actually mixed this up. I think there's a plus sign here. Okay, I can do minus here. So then I'm going to chain rule this, and I'm going to get, you know, f minus f prime plus f prime equals 0, right? So basically it's going to be, you know, so it's satisfied, right? And on the other hand, if I say, you know, there's another solution to the equation, you know, these can happen, you know, but this boundary condition won't satisfy that. Or another way we can look at it is, actually, no, I'm of two minds, because this, you know, derivative along t minus r actually does make some kind of sense, because we're sort of, what we end up having is that as you move, what we want to have happen if there's just outgoing wave is that, you know, if you move along, you know, the peak, right? You know, then you want you know, the derivative, you know, time derivative sort of moving along in that null direction, right? Where you're moving along with the peak of the wave, it shouldn't change, right? Because the whole thing is just supposed to add that. All right, so why?
We can continue the discussion, but
Yeah, I got some kind of sign mix up in my head. Hopefully you can sort of see where I'm trying to go with this.
part of the point of my question is that in numerical classical field theory, there have been two approaches that come to mind. One of them, again, how do you formulate absorbing boundary conditions? But there's another approach, which is how do you formulate numerically radiation boundary conditions? That is, through a transition to something that makes an infinite domain so you get no reflection. Both of those have their place in different numerical computations, so we can talk about that some other time.
Okay, yes, I wasn't aware that there was so much significance to those two different words. Now I see why Louisa was always insisting on saying we have absorbing boundary conditions. Because I mean, that just sounded like a weird way of phrasing it to me. The outer boundary is absorbing the wave, but it is, you know.
Right, yeah, question about that was interesting about the cylindrical symmetry, axisymmetric, and then in your simulations, the turbulence got averaged out. Is that something you also see with hydrodynamics and things like that, or was it particular to the electromagnetic stuff?
I expect that it's going to be pretty widely true in hydrodynamically. As a matter of fact, you know, one of the things that it's probably more true in hydrodynamics than in MHD, right? Because it's in the magnetically dominated region where we're able to have these large scale fields where you can get sort of a a large scale axisymmetric structure, right? And you collimation of outflows, you know, along the pole. You know, I've always kind of had this, had some ideas for things I wanted to do in the hydrodynamic case, you know, making these models. One thing that I thought would be particularly fun is, you know, so basically there are two things that you might want when you talk about a 2D simulation that mimics 3D, right? One is your 2D simulation mimics 3D with one dimension averaged out, right? And I think that for turbulence, that often becomes very boring, right? Because you average out the turbulence and you replace it with some transport term. So the other thing that I got ideas for how you could do is suppose you wanted 2D simulation that mimics a two-dimensional slice of a 3D simulation, right? That has the statistical properties of a 3D simulation, right? So turbulence cascades to small scale rather than large scales like it does in 2D, right? So in that case, you'd have to adjust the evolution equations in a very different way, right? And it's actually, you're very restricted on how you do that while respecting the scale invariance of turbulence, right? So it's a fun problem, you know, that I couldn't convince Courtney to do because she said, no, we'll never finish it in time for my degree. And she was right. It would have been a disaster if we would have gone that way.
Thank you. Wonderful talk.